Olá a todos and welcome to another Julia video of the channel. This is one of the first videos that I'm doing that is not related to optimization. I will start doing videos like that if this video is liked by people. In English at least. In Portuguese I have many of those videos. This video is actually related to tabletop RPG, a puzzle in particular. So this is something that I created for my players. I took out a lot of the fantasy, but I left the basic ideas of what the puzzle is. So while creating this puzzle, I was wondering, does this have solution if I change things a little bit, learn a little bit more about modular arithmetic and how it applies to this puzzle. And I found that very interesting because it mixed modular arithmetic with linear algebra. I was eager to try it on Julia and it worked. So this video is essentially the introduction to what is modular arithmetic, how does it apply to our RPG puzzle, and how can you implement that on Julia. If you find some of those things are basic, you can use the chapters below to skip ahead. But I already ask you to like and subscribe. And if you can comment below saying if you like the video, if this subject is interesting or not, or suggestions of new topics, that will be very helpful for me as well, okay? Thanks and have a nice video. We'll talk later at the end. Okay, so let's start talking about our RPG puzzle. So we were playing the game and I came up with this, I thought at the time, clever puzzle. Simple enough to be solved by chance, but also complicated enough if people wanted to take some time. The simplified version here, without any of the fantasy behind it, is that you have three symbols, in this case 3 triangles, and these triangles have a mark at some place, and you have 3 dials, and these dials can be rotated, at least that's the initial thing that you can see. When you actually try to rotate the dials, so you start moving the dials moves completely one rotation or 1/3 of a rotation. It doesn't stop midway, and in this 1/3 of a rotation that it does, it moves the symbols. Okay, so it was in this position. You start moving it clockwise and ends up in this position, and you see the symbols moving. If you try to move it again, it's gonna do the same kind of rotations in the symbols. So if you move it once more, it does the same thing. And if you move it once more, all the symbols go back to the same position. Same thing happens if you move it counterclockwise, it just undoes the rotation for each symbol, okay? So it's a simple puzzle. The other dials do the same thing, but different kind of rotation. So if you move this one, it moves the symbols to other places, okay? So it's that's the whole idea. Showing the trace, you can see the whole movement of the symbols. The trace was not available at the RPG game, but yeah. So this is one rotation. And also another important fact, the symbols also rotate 1/3 of the way, 1/3 of the rotation each time. They don't stop midway, okay? So these are essentially integer numbers. And essentially the question was, there is one position that these symbols must be at. So you can imagine they must be all pointing up. Figure out how to make them all point up. So if you want to do it at home, let me just quickly show you what each dial does. So the first dial, if you move it clockwise, it moves the symbols this way, and clockwise undoes that. The second dial moves the symbols this way, counterclockwise undoes that. The third dial moves the symbols this way, and counterclockwise it undoes that. Okay, so you can try at home, solve this puzzle, see how long it takes for you to solve this. Okay, so I imagine you solve this problem. There are quite a few ways to solve it. The simplest one is by just random guessing. If you just move things around, eventually you're going to solve it. If you really contemplate if I move things around, am I actually going to solve it or not? You start to get a glimpse of the solution, which is that these are finite amount of configurations that you have here. And the core of the solution is that you only have 3 configurations per dial. So if you leave it as is, you have essentially the number 0. If you move it 1 to the right, you have the number 1. If you move it 1 more to the right, you have number 2. And if you move it 1 more, you have number 0 again. So you can think of 0, 1, 2 or -1, 1, 2. Okay, so these are all possible ways of solving it. That's it. So you have 3 possible ways. 3 times 3 times 3, you can guess them all. Eventually you would get it. But this also implies that you can actually try to solve it by using these numbers. So when you move the first dial, you are moving, let me see here. When you move the first dial, you're moving the first symbol once to the right, clockwise. The second -1, and the third one -1 as well. When you move the second dial, you're moving -1, -1, and 0. Okay, so going back is negative, going counterclockwise is negative, and the third one is 1, 1, and -1. And here you have the dials, dial 1, 2, 3. And these all deviate from the initial position that you had. The initial position is the position that it is right now. From the deviation from the way that you want, which is 0 rotation. So it's rotating, well, if I use my mouse it's better. It's rotating a third of the way, right? So it's at position 1 in the start, at position -1, and position 1. So this is the description for the dial rotation, or for the symbol position given the dial rotation, okay? So if I move dial to 1, 1, 1, I can do the math here. If I use 1, 1, 1, it's gonna be, so this is, all of the dials are rotating once. Okay. So the final position of the first dial is 2/3 of the way. The position of this dial is -2/3 of the way. And the final position of this dial is -1/3 of the way. Okay. Remember, these numbers are from standing upright position. Okay, so they are not relative to these green lines here, so they can be removed. So what do we want to do with this mathematical equation? We want to solve it for the situation where the dials are at the upright position. That is, they have 0 rotation. Okay, so that's what we want to do. We want to solve a linear system, and we can do that easily at first. Okay, so down here I have exactly that. So I have these, it should be the same numbers. If you look column by column, yeah, they are all the same numbers. And I have here the initial position 1, -1, 1. If you solve for it, you're gonna have -1, 2, and 2. So this is the backslash. -1, 2, and 2. They are solved. Okay. So that's it. This strategy works. You solve the problem. Everybody's happy. My group actually solved it by chance completely. So they essentially tried the first one and said, what happens if you do the next one? And they tried the next one. And does the last one also moves things around? Yes. And they said, okay, let's try this thing first. So they did 4 movements and solved the thing. And was completely by chance. So yeah, it happens. Okay, so if you found this one easy, it was mathematically easy to solve it, I have a better one for you. It's the same idea, but now you have 5 dials and they all turn a fifth of the way when you turn them. So essentially 5 positions, you have 5 to the power of 5 positions to try. So brute forcing this one is much harder. You can always do it. And the fun part here is that I actually have like a generator of puzzles. So this is with seed 1, 2, 3, a puzzle with 5 positions. So if you want, I can make this code available and you can try this around. And here you can see what is the matrix that runs this puzzle in the back end, I guess. Okay, so if you want to solve this puzzle, this is how it works. When I move the dial once, the first column is moved by -1, so once to the counterclockwise. So let's show the trace, move the first one. So -1 is once to the right, to the left, sorry. -2 is once, twice to the right. I'm saying completely wrong, but your guess. -2 is counterclockwise twice. 2 is clockwise twice. 0 is 0. -1, etc. So you can just use these. And 0, 0, 2, 0, 0, 2 minus 2, 0 is the initial position. Okay, so you can try to solve this at your own time. And one interesting thing is that our approach of just using a linear algebra doesn't work, because it wants you to use floating point numbers instead of doing full terms. And that's where things get interesting. So our basic approach of just trying to use the backslash solver doesn't work. And the reason it doesn't work is because it doesn't take into consideration that we want integer solutions for that. You can't just round those things. I think actually, but I think they are all close to 0. This is 0, 0, 1, -1 and 0. 0, 0, 1, -1. Phew, doesn't work. That would be sad for me, but yeah, if it worked. So the question is, what can we do instead? And there's something called modular arithmetic. I'm not gonna go into the details, but essentially is you realize that what you're talking about here is representatives of all the possible rotations that you can do. So you can do rotations in this case in 5 different ways. Either you don't rotate a fifth of the way, 2/5 of the way, 3/5 of the way, 4/5 of the way, or you go back to one of the other 5. Okay, so these are essentially all of the reminders of the division by 5. 0, 1, 2, 3, and 4. Again, you can think of these as -2. Oops, sorry. You can think of these, instead of 3 and 4, you can add -2 and -1. But this is exactly the same. All of the math is going to work out the same. In many cases, it will be more interesting to use the negative numbers, but in most situations, this is the fun part. And whenever you think about any integer number, you're gonna consider the remainder of that number by 5. So whenever you do an operation like 9 plus 12, you can do the translation immediately. So 9 is actually 4 and 12 is actually 2. So the reminders of the division by 5. Or you can just do the math, 21, and then convert. This is actually 1, the remainder. Or you just do 4 plus 2 is 6, and the remainder is 1. This is a plus is equal, okay? These are all the same. So each one of these numbers is a representative of all of the numbers that reminder. The fun part is that not only sum works, you can also do subtraction. So addition and subtraction are essentially the same, but more interestingly, you can do multiplications and divisions. So let me erase this here and consider a number such as 3. So 3 times 0 is 0. Nothing interesting there. 3 times 1 is 1. 3 times 2 is where things start to get interesting. So this is 6. But 6, for some reason I said that 3 times 1 is 1, but 3 times 1 is actually 3. You also thought that you were crazy for a while, right? But no. 3 times 3 is 6, which is actually 1. 3 times 3 is 9, which is actually 4. And 3 times 4 is 12, which is actually 2. And all of the numbers are there. So you have on the right side 0, 1, 2, 3, and 4. Okay. So this is very interesting. And this is just multiplication. You can think of these again as rotations. So if you take the 3 parts rotation, the 3/5 rotation, which is 1, 2, 3, this operation here, and you do it 3 times. So this, you're gonna do 1, 2, 3, 1, 2, 3, 1, 2, 3. And this is the same as going back once or going forward 4 times. So that's why this is 4. Okay, it works that way. But what's even more interesting is that you can define the division of the number here by looking at the inverse of a number. So one way to talk about inverse is the inverse is the number such that if you multiply by that number, you're gonna find the number 1, right? So if you take any of these numbers and you multiply and you have 1, then one of those numbers is the inverse of the other. And we have that for number 2 and 3. So actually the number 2 is the inverse of number 3 and vice versa. So 2 inverse is 3 and 3 inverse is 2. Okay. And one way to define division. So how do you define division? You just do A times B inverse, and so you have division by just doing multiplication and using the inverse. Question: does the inverse always exist? In this case, the multiplication is quite easy, but does the inverse exist? But you need to use a prime number to do the modulus thing. So if you do a rotation with just a square, like you have 0, 1, 2, and 3, it doesn't work. Okay, so you can get to situations where you don't have any inverse. So if you do like 50% rotation, if you do it twice, you're back to where you were. So if you do it 3 times, 4 times, any amount of times, you're never gonna find 1 here. So it doesn't work for any number, any polygons. You have to use a prime number of sides, okay? But let's not worry about that. Let's just consider our case. We have 5 sides. So for 5 sides, everyone is happy. It always works. And because of that, you can solve linear systems. Okay, since division works, we can now solve linear system using these numbers. So let's get a quick example here. For instance, 3, 2, and 4, 4. Why not? Multiply by x, y equal to 1, 1. For no reason. We can actually check that this is a valid system, so we should check that the matrix has a determinant that is different from 0, and the determinant here is just 3 times 4 minus 2 times 4. 3 times 4 is 12, minus 8, this is 4, and 4 is not 0, even in modular arithmetic. Mod 5. Okay, let's solve this. How do we solve this linear system? I'm gonna use Gaussian elimination because it's something that's very easily translated into a more general method if you need to implement that. And the way to do it is you take row 2. I'm using L for line in Portuguese. Line, but anyway. You take row 2 and update that row, subtracting a multiple of row 1. And what you want to do is make this number here, eliminate this number. So you want to make a 0 appear instead. So in that position you want a 0. And you're gonna use a 4 and a 3. So the number M21 has to be 4 divided by 3. Usually it would be 4/3, but not in this case because we are not talking about fractions. We were talking about division. So how much is this? So 4 divided by 3 is actually 4 times 3 inverse, and we saw 3 inverse is actually 2. So this is 4 times 2, which is 8, which mod 5 is 3. So that's what we're going to do. We're going to multiply the first row by 3, and we're going to update the second row by subtracting that amount using the augmented matrix here. The second row is 0. I'm not going to do the math here. You have to trust that we did everything correct. 4 minus 2 times from the first row, 3 from M21. And the right hand side is 1 subtracted of 3 times the first row as well. Here for consistency I should say 3 times 2, but anyway. This becomes 3, 2, 1, 0, 3, 2, 1, 0, go! And 4 minus 3 times 2 is 6. 6 is actually 1. 4 minus 1 is 3. And 1 minus 2 is negative 1. And negative 1 is actually 4. So that's it. So I did a small mistake here, which eventually became a bigger mistake, So just so you know, this is the magic of editing. 1 minus 3 is negative 2, not negative 1. And negative 2 is actually 3. So this is 3x plus 2y equals 1. And 3y equals 3. So 3y equals 3 means y equals 1. And 3x is 1 minus 2, which is negative 1, which is actually 4. So x is 4 divided by 3. 4 times 3 inverse. 3 inverse is 2. 4 times 2, this is 8, which is actually 3. So 3 and 1, does it make sense? This is 3 times 3, 9, plus 2, 11. 4 times 3, 12, plus 4, 16, which are actually 1, 1 when in mod 5. So it's correct now, but I did quite a few mistakes and had to backtrack a lot. So don't trust my math. Usually don't trust my math. Okay, that's it. That's how it works. We can actually just implement this and see it working on Julia now. So the first thing that we're going to do is create a struct for mod n numbers. I'm gonna call it mod n. So this is the structure complete. I have a struct mod n, which is a number. It's gonna have a value. And this is a constructor for this new structure. You can notice that we have a parametric type. Instead of internally storing this base, I decided to use a parametric type. It makes more explicit that we have this type. It's not just value for a structure, it's part of the structure itself. So I think it makes more sense to be a parametric type than just an argument, so that just a field. But anyway, I'm using the function isPrime, which is from the primes package. And if the number that I give is not between 0 and n minus 1, when I call the mod function, it's gonna be. So I'm creating a new number, which is gonna be in the correct place. If it's not a prime number, it's an error. So here's some examples. Mod n5, this is the structure. If I call it with number 3, it's just number 3. If I call it with number 7, it's number 2. If I call it with number minus 1, it's number 4. Okay, that's the basic of it. So the first thing that I want to do is to make sure that we always visualize these numbers in a nice way. So I changed the way that these numbers are shown by specializing the show function for the type mod n. So when I have one of these numbers, so here are 3 of them, they will appear as the number that they correspond in that base, in that mod n thing, with the subscript correctly. So if I say mod 5.3, you know what it is. If it's mod 7, it's gonna be different. If it's mod 11, it's gonna be different. Okay, it always shows it in a nice way. This function is not very complicated, except for this part. So I googled it to find exactly this part here, which helped a lot. But yeah, not gonna try to explain the details of it, but essentially it's a Unicode kind of thing. So next we want to actually implement the operations for these numbers. So import these operators. So when you are doing function base.show, it's obvious that is from base, but when you're doing with the operators, is you do the import separately and then you do the function, because it's nicer to see. It gets complicated to see, and just gonna show the first one. So if you sum 2 mod n numbers, x and y, you have to say where n. The sum is gonna be just a new number, and since I'm doing the mod in the constructor, it doesn't matter that this is within the bounds or not, within the actual constraints of 0 and n minus 1. And this is one of the reasons why n is a parametric type. If this were not explicit here and it was instead of like a base number, I would have to check here that the base is the same. Here is just a type, so it's always there. It's always it's type stable, essentially. That's what I'm trying to say. But if you don't know what type stable means, it gets complicated. Let's not do that. So plus is done if you try to sum 2 numbers, 3 and 4. This is actually 2. So 7 mod 5, 2, it works. If you try to sum numbers that are not in the same, well, these numbers don't exist, but if you try to sum numbers that are not in the same base, there is no sum for that. So it's the same as trying to sum 2 numbers that somebody created from thin air. It doesn't make any sense. So these are the other operations using the magic of editing. The only thing missing is the division, but to do that, we're gonna first do the inverse. So the inverse of a mod n number, where n. So the inverse is essentially finding which number between 0 and n minus 1 that when I multiply by x is gonna return a 1 for me. So I can just see if x is 0, and in this case I'm gonna error. Oh, 0 has no inverse. And then I'm gonna do a for between 1 and n minus 1. So if mod n I times x is equal to probably easier if I do this like dot value equals to 1, so I don't have to worry about things like that. If this is the case, I'm gonna return mod ni. Okay, it compiled apparently, so here we should try the inverse of mod 3. So here I just noticed that if x is 0, doesn't make sense. It has to be x dot value. So the value is 0, no, so it works. So for mod 5, the inverse of 3 is 2, and we can actually do it for all numbers. Remember, I can use Julia dot operation to broadcast to this array, this range. So the inverse of 1 is 1, the inverse of 2 is 3, the inverse of 3 is 2, inverse of 4 is 4. I like this one, the inverse of 4. 11, it should work as well. And that's it. Because of that, we can define the division by just using the inverse. So the division x divided by y is actually just x times the inverse of y. And that's it. We have all the 4 basic operations now. One extra thing makes our life a little bit easier. The opposite of a number as well. That's just the opposite inside the model. Okay, now truly we can move to something a bit more interesting. You don't have to do this, but I always like to do it. If I create a new number, mod n3, and I just try to add 1 to this number, it doesn't work because the operations are only working for mod n with mod n. Okay, so they require 2 mod n's. So you can actually do something with metaprogramming. So actually, interrupting myself here, I was watching it back and I noticed that there is something better to do in this case. You could do instead a promotion rule for integers. Essentially what you want is if you have a number which is an integer and not a mod n number, you can promote it to a mod n number by simply calling this constructor on the number. So this happens because we have a constructor for mod n which receives an integer. So we can create something base.promote rule for the type mod n. So if you receive a mod n and an integer, of course var n, you can say, yeah, use mod n here. So this will call mod n for the integer, and everything will be all right. So saving here, you see that it works already for our mod 5 3 plus 1. And just so you're aware, you have a promote that you don't directly edit. Okay, so you add promoting rules for your numbers. So this becomes a number in the mod n structure. So going back to the original video, ignore the metaprogramming code that you see. It's supposed to be just promote rule and everything else works just the same. And finally, it comes to the part where we are actually trying to solve the linear system. Let's just create a simple matrix here. So if you do a rand mod n, let's do a rand of 0 to 4, 3 by 3 matrix, and I'm gonna convert everyone to mod n. Okay, so actually use A for additional matrix notation. So A and B are here. Okay, you can see them here. Doesn't make a lot of difference, and I'm not using a seed, so they'll always be different. If I multiply these, they just work. So matrix multiplication internally will call the element multiplication, so they work. If I subtract by another vector, they work as well. So I can actually just take that initial problem and try to solve it directly here by implementing my own Gaussian elimination, and it should be reasonably easy to do so. Okay, so this is the implementation of a simple Gaussian elimination algorithm. I'm making copies, so I don't have to worry about modifying these parameters. First I eliminate, then I substitute back. The algorithm has no pivoting, so I am assuming a lot of things, as you might know. Let's try with a random matrix to see if this works. So I'm creating a matrix A, a vector X. We create B equals A times X. And when we call Gauss elim, so this should be our solution, I can compare X and Y. So here you can see for this particular problem, computing the solution using Gauss elim, the difference between X and Y is 10 to the minus 15, which is essentially 0. Okay, so it worked. It did a good job, and it found the solution reasonably well. So just in case you're not believing me, I can just show both of the vectors as well, and okay, it works. Instead of doing this, I'm gonna do this mod n, and here I'm going to get a number between 0 and 4 here as well. So first, same idea. If I do A and X and I create B equals A times X, when I do A times X minus B, it should be 0, so I can use that for comparison as well. But first what I want to do is compute Y, which is the Gaussian elimination, and it failed. Why did it fail? Because 0 has no inverse, so we're gonna have to set seeds. So let's use seed 0 first. Doesn't work. Seed 1 doesn't work. 2, 3, seed 3 works. Okay, it doesn't work because we're not doing any pivoting. I solved this. Now I can check X and Y. They should be the same vector, and they indeed are the same vector. Okay, remember you can compare this using norm. You can do norm. X, A times X minus B, A times Y minus B. So finally, we have a situation where we actually solved the problem using Gaussian elimination. We implemented Gaussian elimination in a completely general way, so it doesn't actually knows about or mod n type. Actually, if you try to just use something else instead of our Gaussian elimination, like if you do y equals a backslash b, it's gonna fail. Okay, so actually fails if you use just a normal backslash operator, and that's a pity. But we actually can fix it, and to fix it we actually only need let me see, I think 3 functions, and we're gonna create them now. So the first function that we need is the ABS function. So ABS is the absolute value of our mod n. Well, if the numbers are only positive, if you only consider numbers between 0 and n minus 1, we can just say that it's gonna be x itself. Okay, so we can do that. Okay, so I just ran it here. It works, but actually you have to press play here because of the way that Pluto works. This is not necessarily running before this because there is no explicit information between them. So when I run this and then I run this, it knows that it's in order. Otherwise, you can also move this back to here, or to Gauss elim for that matter. Yeah, or to do it here so you can see everything going on at the same time. So the second function that doesn't exist for our type is the function isLess. So what happens with the isLess function? We're just going to use the values, and then we can play this. And now it complains about another function which is the function conj, which is the conjugate value of our number And our number is real, so it doesn't have a conjugate values. Or actually the conjugate value is just the number itself. Run again. And it works. So with these three definitions, which are a little bit out of scope, I guess, of what is accepted in modular arithmetic, I guess. But with these three definitions, we actually made the Julia backslash operator work for our new type. And now we can actually solve all the way back there. Here, we can actually solve our problem. And it says it should be 4, 3, 4, 2, and 3. We are actually using numbers between -2 and 2, but this can also be easily solved here by using numbers from 0 to 4. And now we have 4, so it runs, the trace might be nice just to see. 4, 3, 4, 2, and finally 2, 3. It works. The trace is not nice at all. That's it. So all you had to do to solve our puzzle in our RPG was implement this in Julia. In a few hours, you will have the solution to the puzzle. It will not stall the game at all. Okay? So this is a silly example of how to solve like a fun problem that you're playing in the moment in a kind of convoluted way, but that's math for you. But the thing that I like about this is how expressive Julia is for these kinds of problems. We created a new type and we made it work with Julia's internal backslash operator with 3 new functions for this type. And this was less than, I think, 50 lines of code. I implemented my own Gaussian elimination, which was not required. And some of these things were like niceties, like showing in a nicer way and making the arithmetic operators work with integers, not only with their own type. So it could actually be even less than 50 lines of code if you actually want just the bare minimum of code. So I hope you like this video. I essentially am always looking for more places to apply Julia. So whenever I have a chance, I try to do something. If you like this kind of content, please like, subscribe, press the bell button, and leave a comment so I can know your thoughts on this subject. So thanks for following, and I'll see you next time. Ciao.